Okay, so I think I am audible, right, everyone? Can someone respond?
Yes, sir, you're audible.
Okay, okay, great. Let me know if you're able to see my screen. I hope you guys are able to see the screen. Yeah, okay. So I will once again welcome you all for this analog IC design training, and I congratulate everyone for taking this bold decision in enrolling yourself for this training. And today being the first session, I'll try to give you the overall briefing about the entire session, how exactly we're going to take the session forward, and what all the things you're going to learn, and how this entire analog IC design training would be very helpful in your journey down the lane, and what are the things that you can gather from this analog IC design training. So this couple of introductory sessions, maybe one or two sessions would be theoretical in aspect, and then down the lane we'll begin our entire session on the hands-on mode, where we will try to ensure that you will be working on the Cadence tool. So the Cadence tool, whatever I have sent you as an Google Drive link, I hope you have downloaded that, and down the lane we'll try to ensure that we'll get into those entire aspects of learning the things through the simulation. Now let's try to understand why this course is different, and what is the course description and what is that you're going to do. Like I told, we're going to understand the core topics in the analog IC design, which is going to prepare you for all the real life challenges design of the complex and analog mixed signal blocks. And what does that mean? That means it is going to beneficial for your upcoming placements, or maybe for your job hunt. And since you are working on the real-time projects, you can portray those projects as an mini projects or capstone projects in your resume, and ensure that you grab the opportunity. So that would be our core intention. See, our intention here is to ensure you guys understand and learn the things as much as possible in a simplified manner, and you should be able to reproduce the content whatever you have learned. So I expect everyone to understand the concept. Just don't listen it, and don't forget it. Try to practice it on your own, and then only you'll be able to understand, and you'll be having grip on these entire concepts. Otherwise, merely just listening, it would be just like any other course, any other training, right? So here our focus would be on the CMOS circuits. Here we'll be trying to focus, or we'll be trying to speak with respect to both analysis and design aspects of any circuit that we're going to design. And that's when we ensure that we'll be undergoing a strong hands-on component, and that's how we ensure that you come up with a strong design concepts. And in due course of time, like I told, we will be using the standard industry standard tools. Now, here we are going to ensure that a flipped classroom model is being utilized, wherein we are going to, I'll try to float some of the questions or some of the queries even off the record. Maybe you can just go through those contents in your free time, and during the session, it will be very helpful for you to understand the flow in a much easier manner. So we can have a core conceptual discussion in the entire session, rather than merely discussing all the concepts once again during the session. So our focus during the session would be such that we will be focusing more on the hands-on contents, and the required theoretical aspects would be covered over here. All the certain other extra contents or extra conceptual contents, I'll be trying to float you through the offline mode, maybe in the WhatsApp group, so that you can go through them in due course of time, and during the classroom sessions we can have a fruitful discussion. And like I told here, though you are attending the training in online mode, we are not in the classroom, but still we're going to track your progress continuously, and we're going to give you the real feedback on your work. So the feedbacks would be very, very harsh if you are not going to come up with the contents. Harsh in the sense, it's not that we'll scold you guys, something like that. Harsh in the sense, we'll be entirely describing you where you're going to land up in your near future based on your current progress. So ensure that you utilize these entire 8 weeks of time so that you come up with a proper, if not 100% analog design engineer, but at least 10 or 15% of the contents, whatever you are going to learn over here, try to ensure that you are having grip onto those contents. Now, why this course is different? Like I was mentioning, we are going to ensure that we are going to design the entire circuits through the analysis by inspection skills. We'll do the hands-on and theoretical concepts using the hand analysis and circuit simulations. Of course, we'll be using the industry standard tools, and then we'll try to do the projects or the assignments right from the specification stage till the outcome stage. It's not that we'll randomly design a circuit, because it so happens that maybe in your labs and all, you'll be designing some of the circuits. There, the problem statement would be given. But the question why such problem statement is given, nobody will explain. So we'll try to gather the inputs from the design specification stage. Sometimes that also becomes very important. And from there onwards, we'll try to jump into the design stage. So that's how this entire course is different from the other or any other analog IC design course. And these are the references that I will be referring. I'll definitely share you this recording and this uh, sheet, so you can just go through them. And the Razavi book is the one which I'll be treating it as a Bible of this or Bhagavad Gita of this entire course. And then the other references could be your Cedra and Smith, Floyd and other. This Razavi book rarely I'll be referring, but this one and this one, the first reference and the first textbook, is something that I'll be frequently referring to. Okay, fine. So now let's try to get into some of the very fundamental things before we actually get into the MOSFETs working, which I'll be taking up maybe in the tomorrow session. I'll start with something called as Moore's law. And I hope everyone has come across this law. That's a very famous law. Now, what does it says? It says that the transistor count doubles every year. It simply says that every year the transistor counts doubles. Now, what does that mean? That means that, let's say that in the year 2024, one IC was fabricated, and in the year 2025, the same IC has been fabricated, and in the year 2026, again, the newer version of this IC is fabricated. Now, what makes these three ICs different? Of course, the year of manufacturing, but most importantly, the number of transistors. So the number of transistors in the IC which was designed in 2024, let's say that if it's having 100 transistors, now the IC in the year 2025 would have 200 transistors in it, and in the year 2026, 400 transistors in it. So that is, or roughly, approximately double the previous year. What does that mean? That means the technology is increasing rapidly at such a rate that we are in a position to scale down the structure of MOSFET, or for that matter, transistor, which happens to be the very fundamental core component of your any integrated circuits. Now, what does that mean in turn? Again, let's try to break it down. We'll try to ensure that we'll understand those things down the line. But the thing is scale down in the sense, if a transistor is performing, let's say that I'll give one simple example. If a transistor is performing to give a current I of, let's say, 10 microampere this year, now the same transistor they would redesign in such a way that it is going to consume lesser area, yet giving more current in the coming days or in the next year. That means the technological trends are being increased at such a rapid rate that at a small or at a same given area, we are trying to produce or we are trying to achieve much better performance than the previous area. And what does that mean? That means if I have an area of 10 micrometer by 10 micrometer, wherein I can place, let's say, some 10 ICs to give you some definite functionalities over here. Now, in the next year or in the subsequent year, I will be able to utilize the same 10 micrometer by 10 micrometer die or the area. I can place even more ICs, and when I place more ICs, what does that mean? The performance is automatically increasing. That means with an effective area being remaining same, I am still able to increase the number of ICs, which in turn means that I am still able to increase the number of transistor counts on the same area. Thereby, it is going to enhance the performance. So earlier, this Moore's law was something like this. It was basically, it was not counts double every year. It was approximately for 18 months. Now the technology has increased at such a rapid rate that every year the transistor count is doubling. And you may ask the question, is there any end to that? Because see, if this year there are two transistor, next year it will be four, and like that it keeps on doubling, and it's an binary exponential growth, and definitely there has to be some end, right? And of course end has already reached or it is about to reach, but the enormous advantage that this scaling has given, so scientists are able to get some other they are trying to do the experiments, and they're still trying to get the enhancement in terms of the performance. So the meaning is very simple. Basically, the transistor, which is our core component, is becoming, or it is rapidly increasing at such a rate that we are very much reliable on the MOSFET, and in the coming days, the understanding of MOSFET becomes very important for a successful analog IC design engineer. Now the question, so this is what I was telling you. So down the lane in the year, I think most of you guys have come across this chart in many of the textbooks. So if you see, these are the Intel processor names, 4004, 8008, 8080, 8086. So the number of transistor counts which are mentioned over here on the y-axis, if you roughly see, it has seen an exponential growth. And I have not mentioned till now the processor has reached till i7, right? It is in 2024-25. So this has gone even more. So even more number of transistors are being placed onto that, and the meaning of that becomes very clear that more transistors means more performance. So that is basically the major breakthrough that everyone is achieving, and that becomes very important for any successful IC design engineer. Now, so like I was talking, the scaling of MOSFET or the MOSFET sizes are getting reduced. Now, how do you define the MOSFET size? Like here, they have mentioned something called as feature size. If you see over here, right? Minimum feature size. It is shrinking 30% or approximately 1 by root 2. And there is no formula to that. They approximately calculated that, and they somehow figured out that it is approximately shrinking 30% every 2 to 3 years. So that's what basically, like I told, the Moore's law was approximately close to 18 to 24 months earlier, but right now it is getting quoted for every year. That means it is shrinking every year by 30%. Now, if you see down the line in the 1970, the feature size, I'll tell you what exactly the feature size. If it was 10 micrometer, and if you come down and see the technological trend, it has reached till the nanometer. So now it has reached 22 nanometers. In fact, it has reached 5 nanometer, and even 3 nanometer nodes are being worked upon in many of the companies where the MOSFET sizes are very, very small, and there are a lot of different challenges that it has on its own. So the MOSFET, which works at 10 micrometer feature size, doesn't have the same challenges at 22 nanometer or at 5 nanometer, because the sizes have reduced drastically, and there will be enormous different second order effects that would be happening within that smaller sized MOSFET. Now, when I say the feature size, let's see, maybe I have included in the next slide. So feature size, yeah, if you see, usually feature is something, one of the characteristics of your MOSFET. So let's say if I have the small cross section area of the MOSFET, and let's say this is source, this is drain, and by the way, I am taking an N channel MOSFET. Now, this being the length of the channel. So, and of course, here would be your gate. Now, earlier, how exactly we used to define the size of the MOSFET? It was basically the length of the channel. So, length of channel defines MOSFET size, and this was in earlier days. Nowadays, that means if I say if the length of this MOSFET channel is 5 micrometer, that means I can clearly say that I am working at a 5 micrometer technology. If I say it is a 45 micrometer or 45 nanometer technology, that means I am working at a 45 nanometer technology MOSFET. That means the length defines the technology. So usually you might have come across the term, see, the technology nodes, right? If you come across the term 22 nanometer technology, what does that mean? Generally, that means they are talking about the length of the channel of that particular MOSFET. So if you say that you have good amount of exposure in the 90 nanometer technology, that means the MOSFETs, whatever you are going to use in that entire circuit, will be those MOSFETs which have the length equal to 90 nanometer. So that is basically the technology node. But now the definition of this length or the feature has changed. The reason behind that is, like I told, these MOSFETs are getting scaled down. See, when I say scaled down, it doesn't mean that I'm just shrinking the size. See, shrinking the size is totally different than scaling the MOSFET. Scaling down or scaling up means you are effectively reducing the sizes of every component which is of the same ratios previously. If I say, let's say the source is let's say is having an area of 2 micrometer square, and the substrate, let's say that it is consuming 5 micrometer square micrometer of area, and let's say that length is 20 nanometer. Now, when I scale it down, I am effectively scaling these sizes such that my overall performance is yet going to remain the same. That means with these sizes, let's say that if the current, because current is the major parameter that will be flowing through the MOSFET, the current through this MOSFET is, let's say, 10 micrometer. That means when I scale down this MOSFET and I change it to, like, let's say 1.5 square micrometer area, and let's say I reduce the length from 20 nanometer to, let's say, that 18 nanometer, and let's say I'm trying to change the size of the substrate also from 5 micrometer square micrometer to, let's say, the 3.5 square micrometer. When I do this entire thing, the current is yet going to remain at 10 micrometer. So that is basically the scaling down. But of course, if you want to change the current also, if you want to gain more current, of course, you can play around with this length and width of the MOSFETs. That again is a different concept. But when it comes to the scaling concept, and somebody says scaling, effectively the performance or the major performance breakthrough is going to remain same, but the sizes are still reduced. So that is basically the scaling. So this is how basically the technology trend. Now, I was talking about the technology node that is prevailing nowadays. Now, I have shown you the picture over here. Now, so these are the some of the maybe uh, the layout structures that they have laid down over here. So usually when we try to build the MOSFET, we try to get the connectivities from these source, drain, and the gate through the metal layer, right? Now what is the technology node that they say is the distance between the this particular metal, or the starting point of the metal, the next metal. So what is the metal? Which we say it as a metal pitch. So that is nowadays being called as a technology node or feature size. Instead of telling as a technology node, the feature size. Earlier, length was our major thing. Nowadays, it is distance between two metals. Now again, how they are going to consider which metals, what are those things? Again, it's altogether a different ball game. But on a superficial note, if you want to understand, you should be aware that the technology, whatever we speak, is not always the length, but more or less length is the one aspect that usually they used to consider earlier. Even nowadays also, some of the companies do consider L as the major feature size or major technology. But other than that, due to the scaling, because see, as and when the MOSFET sizes reduces, the length also keeps on reducing, and it is not effectively good to always quote the length only as the feature size, or the technology node. So they have changed the feature size or naming the technology node with help of this metal pitch. So that's basically how we call with respect to the technology node. Fine. Now, yeah. Now comes the will slowly and steadily progress and inch towards where we want to go with respect to this course. Now, the level of abstraction. So what does that mean? Now, whenever we usually we are going to start our discussion with respect to the device structure. So this is at a device level. Always remember, whenever this such kind of structure is being shown, the cross-sectional structure, when we would try to explain the working of a particular device, the devices could be anything like the semiconductor devices could be the diode, your BJT, or your MOSFET. We usually start our entire discussion by understanding the devices. So these are semiconductor devices. So you should be very clear in understanding the working of these devices. Then once we know the working of the device, we will use those devices to build what is known as the circuit. We place a lot of components along with the MOSFETs. You can see resistors are also being there, capacitors also are being there. Both active and passive components we are going to place, and we will come up with a proper application which is going to perform as per our specification or as per our needs. Now that entire structure, we call it as a circuit. Now, once we have those circuits, we'll convert those circuits into a symbol. So usually you have come across through NAND gates or all the gates, NOT gate. So basically, what is the core content inside those things? So normally when you do it in the laboratories, you used to have some ICs with some 8 pins, 4 pins were here and 4 pins were there. And symbolically, those were represented something like this, right? Now, what is the structure that is present inside? Now, I think by now, the people who are in their 5th and 7th semester, they would be knowing that inside these structures, it is all made up of MOSFETs only. Inside them, it is the MOSFET arranged in a typical fashion, which will do the job of your and structure. Basically, now you would be analyzing all the logical gates with the help of truth table. Now, the expected outcome that whatever you are getting from the truth table is being performed inside this entire IC by these MOSFETs only, and those MOSFETs are basically your schematic or the circuit. Now, when you convert those things in a smaller symbols and connect them together, let's say you have one circuit over here, another circuit. Let's say this is an amplifier, and let's say this is one more comparator block, and let's say there is a Schmidt trigger, and let's say that there is another operational amplifier, and you join them together, and then you get a bigger outcome, which is meeting the specification. Now that structure is becomes your architecture. Now, this is where in the industry people would be working on the concepts. So basically, architecture or architectural design. So that means to come up with a proper architecture, you should come up with this entire individual circuits. And to come up with the individual circuits, you should be knowing the working of these things and how, upon connecting, how they are going to work. So then only we'll be able to come up with the architecture. Now, above that, when we connect different architectures together, we will come up with what is known as a system. So typically, if you want to say a system, a mobile phone or maybe your laptop, which has lot of various structures. So sometimes usually we call these as the bigger ICs also. So a lot of different big ICs are connected together to form a system, and these are in turn or inside them they have a lot of individual circuitry arranged together, and inside the circuitry you will find a lot of active and the passive components. Most of the times you'll always find the MOSFETs. So this is how the level of abstraction is all about, and we will be starting our entire structure. Definitely will not get into the system level design, but we will be in due course of time we will be starting with the device level understanding. We'll move into the circuit level structure, and then we'll use those circuits to build the different architectures. So in this course, we'll at least try to reach 3 levels of abstractions. because getting into the fourth level of abstraction is again it becomes a kind of a thesis work itself, where you are going to plug in a lot of architectures and coming up with a design. So we'll restrict our entire course with respect to three level of abstractions. So that's what I was talking. So our material, in the sense, we'll not talk about this material, we'll talk about the devices, the circuits, and the product here would be how we can join the circuits to come up with various architectural design. So that would be our learning journey. Most of you guys have by now have understood what is an integrated circuit. So various components or circuit elements, they can be put together on a single chip, and that makes your something called as integrated circuit. Now the common question that arises here, I have shown you the resistor, capacitors, and this is a transistor, and even the diode. The diodes are also, if you see the structure, maybe in the laboratories, you'll see something like that. But the IC structure is totally different. Now here, my statement itself says that I can plug in my capacitor or resistors, the capacitors, inductors, transistors, everything together and come up with a design which looks like this. The question is how I can put this entire structure within this. Is it that I'm putting this and same structure over here? Or is it that I'm putting the same capacitor over here? Now, if you see an AND gate or AND IC in your laboratory, which is of this size, and a resistor, both look almost the same size, isn't it? Now the question, how is that someone is going to put the resistor inside the integrated circuit? It doesn't digest, right? So the thing is, we are not going to put the actual resistors. So just imagine putting the actual resistors and actual capacitors and trying to build an integrated circuit. It would definitely consume a lot of areas. And possibly by now, you would not be having the mobile phones of the same size what you are using right now. It would have been definitely size of your laptops, because I cannot put all these components or all these I cannot join all these components and say that as an integrated circuit. So what usually we do, we will replicate the functionality of RLC. Now these are majorly the three components which effectively consume 99% of your circuit theory, isn't it? Because wherever you go, we cannot avoid RLC. At least one of the component would be there in your circuit. Of course, power supplies, voltage, and current sources would be there. Those are the supplies. But the component wise RLC, one of these components or all of these components would be there in your circuit. Now, if I replicate the functionality, now what does that mean? Like, let me give you a simple example. I am using a duster to rub the blackboard, which is the functionality of that being to clean the board. Now, if I don't have the duster, I can replicate the functionality of the duster with multiple ways. I can use a cloth to rub the board. That means my job was to clean the blackboard. That my job is done. Basically, my cloth is getting replicated in doing the job of my duster. I can use papers to clean the board. I can use my hands also. I can use water to clean the completely board. So that means I have ways out to replicate the functionality. So that means what is the functionality of the resistor? Resistor, the functionality is to oppose to the flow of current. That's it. There is no rule that it should look like this. My ultimate goal of the resistor is to ensure this functionality is being met. So if I somehow replicate the behavior of resistor using MOSFET. Now again, why did I use the MOSFET? MOSFET being one of the effectively used transistor which can fit in most of my designs, and it is being scaled down at a very smaller level. That means MOSFETs are being worked at a nano and micro level, and if those MOSFETs are effectively replicating the behavior of the resistor, my job is done. I will never use the actual resistor inside my IC because the job of my resistor is being taken care of by MOSFET. So is the case of your capacitor and inductor. If I can replicate those functionalities or those behavior using my MOSFET, my job is done. And that's how you use all those components and plug in together and then come up with what is known as integrated circuit. Now the question is how? How can I do that? How can I effectively replicate the behavior of R and C? So these things definitely replicating the behavior of R and C. We'll try to look into these things when we effectively start our MOSFET understanding. In due course of time, you'll be able to see how my MOSFET is going to behave as a resistor and capacitor. Inductor portion, maybe down the lane, we'll try to focus onto this at later stage. But effectively, how I can see my behavior of my MOSFET as R and C, we will see possibly in couple of sessions from now. Okay, so that's how basically my integrated circuit looks. Now this symbol signifies the discrete worker versus integrated electronics design. Basically, this is what the figure number one is. This is what basically we use in our laboratories to perform the experiments, where we are using the discrete components. In the sense, we'll be using all the capacitor, resistor, inductors discretely to design our circuit. But whereas in an integrated circuit, it comes up with all these things integrated on a single simple device, which is called as integrated circuit, right? Now, like I was talking, what are the components of the integrated circuit components, which are basically the transistors, capacitors, resistors, inductors. And this slide basically talks about how many numbers of these components are being utilized. It all depends on what kind of application you're going to design, how you're going to use those things. So basically, RLC and transistors are the core components of your integrated circuits. Okay. Now comes the interesting things. What kind of signals? Now, till now, we saw the components and the devices to some level. But the question is, what kind of signals are being utilized in our entire devices? And preferably, why do we call circuit design as always analog circuit design and not the digital circuit design? So the reason being, long ago there was no concept of nothing called as digital signals. All were the analog signals, and most of the works were being done with respect to the analog signals only. And analog signals are basically the continuous signals, and like you know, the digital being the discrete signals, as you can see over here. Now, because most of the signals or most of the works that were started initially, that was with the analog signals, hence the name became more relevant, analog circuit design, and that name has been still prevailed. Because normally when we actually see the real life signals, I'll come to this. The real life signals, whatever we see, they are always analog signals. If you see the voice, light, temperature, pressure, if you measure those signals, they're random signals. They're not the digital or discrete signals. And that's the reason why we use the term analog IC design. And we always need an analog interface circuitry to connect between our physical world and our digital electronics, right? And that's how these digital components are becoming most prevalent nowadays. If you even use the digital components, even whatever the components are being used as a digital, down the lane will be always the analog signaling only. So this is the reason why we go for analog. But the reason why we went for digital, so digital, the era of digital started because they were effectively less sensitive to noise. easier to store, easier to process. They are good for automated design, easier to port from one technology to other. Now the question is, or the you may ask the question, how they are very good for the noise. How, of course, for storage purpose we know, but the question in the first one, how they are effectively less sensitive to noise, and how they are easier to port from one technology to another. We'll try to address some of these questions in the upcoming sessions when we actually get into the actual design aspects, where we'll be using both analog and digital components. Okay, so but this is the reason why the digital components came into picture, and those digital components were acting as an interfacing elements between our real world and the digital storage elements. And even though when we work at a core level, or at a level of digital design, but we will be effectively working at an analog domain only, because our actual or real world signals are still analog. Now, this is one such example where we usually say how the physical world and digital processing and storage world is connected through a lot of intermediate components, and this is where your architectures or architectural designs will come into picture. And till the time we are on to the analog signaling, there will be enormous job opportunities for both analog, mixed signal, and RF designers. What does that mean? Analog design is one where you are going to use only analog components and analog signaling. Mixed signal designing is the one where you are going to use both analog and digital designs. RF designers are those designers which are still working on mixed signal circuits, that means analog and digital, but they are using the radio frequency components, or they are working at a radio frequency spectrum. So at that level, basically they are working at a very high speed, gigahertz level, where, because the speed matters a lot, then your circuit performance or circuit design aspects will change slightly as compared to your low speed design or low power design. So that's how your RF designs will come into picture. So broadly speaking, your any job role, whenever we see something called as circuit design or circuit designer or analog design. So for you guys, whenever you start your kind of career, or analog and mixed signal designer, which we usually call it as AMS, right? Or IC design engineer. Sometimes in some of the countries they call by this name. All means same. So by the end of this course, you will be most suitable for applying for the job roles pertaining to these things. So one and the same. RF, it comes by practice, it comes by exposure and experience. Of course, you have to work at a pretty higher frequency components, and the designing aspects for RF design. Very few designers are present in the entire nation, and design is very complex over here, and you have to be very um, careful, and you have to be very skillful in this RF design journey. So this is basically how your entire signal processing chain, and how your job roles, how you effectively connect your devices, why digital and analog components would come into picture, how the circuit goes from circuit stage to the architecture and to the system stage basically looks. And finally, if I just want to come up with the fag end of this first session, why we usually go with the MOSFET technology, and in that particularly, why we go with the CMOS technology. Here I have given you on a superficial note, but definitely I'll try to give you the more inputs in the upcoming sessions. But on a basic level of understanding, like everyone might be knowing now, what is your CMOS technology? It means the complementary MOSFET, and it combines both NMOS and PMOS. And we always have come across this particular uh, points that why CMOS technology is better than the earlier BJTs, which are your bipolar junction transistors. And I think everyone knows that they require very few devices that can be scaled down easily. Fabrication cost is less, and they are faster, and they are effective than the BJTs. So that's the reason why BJT was overthrown by your MOSFETs, and then MOSFETs become very prevalent. And nowadays, MOSFETs and they have gone beyond that, something called as FinFET, which is an advanced version of your MOSFET only. Now they are prevalent. Now, how these are effective than the BJTs? Again, we'll try to address these things down the line when we try to address some of the advantages of the MOSFETs in the due course of time. You will only come to know why CMOS technology is very, very frequently being used. And in that, I would like to highlight one important feature. Now, maybe in any of the interview or someone asks you, among BJT and MOSFET, which is the one if you prefer? Now, my answer would be always BJT, because BJTs, as an individual designer, for me, the speed matters. And when it comes to the speed, it is always the BJTs that was or that had an upper hand, or that is having an upper hand as compared to MOSFET. But then what made BJT overthrown by the MOSFET is due to the continuous scaling. Scaling in the BJTs was becoming more and more complex than your MOSFET. Because of this major region, because we want to always place more number of MOSFETs in a small area, thereby I can get the performance upper hand, or thereby I can enhance the performance. And because of that, people started to scale the devices. And when they started, BJTs were not able to support that much level of scaling. And that is the reason why we went with the MOSFET. But otherwise, BJTs are always superior than the MOSFETs. Another advantage of MOSFET is that apart from scaling, MOSFETs can work at tremendously low supply voltages, because like I told, once you scale down the MOSFET, like I told, effectively you will be scaling down everything. Even the supply voltage also gets scaled down. So if a MOSFET is working at a 5 volt for let's say that 45 nanometer technology MOSFET, then the same MOSFET, if it is scaled down to let's say 10 nanometer, my supply also would be reduced from 5 volts to let's say that zero point 0.8 volts, and effectively my threshold voltage. So at a lower voltages, my MOSFETs can work better, and that is the reason why we went with the MOSFETs as compared to the BJTs. Some of the challenges with respect to the analog IC designs, now that we have figured out, we will be focusing our entire design with the MOSFETs, and the signaling mode would be both analog and digital. Now comes the challenges, which we're going to address it down the line again in due course of time when we actually get into the real-time designing. The supply voltage scaling. See, these are all the challenges when we actually go at a system level, not at the circuit level. But majorly these will be at the system level, and because we'll not be getting into the system level, we'll be at architecture level or at the circuit level. Some of these would be irrelevant as of now, and the major relevant things would be our PVT and variations, supply voltages, these two, and the power consumptions. These three would be our major concerns or major challenges that we'll try to address. And when I say PVT variations, it is process voltage and the temperature. All these three variations, how it is going to impact the performance, we'll try to address that. I will try to give you some insight about the PVT variations. Now here I have put it in a simple pointers. I'll try to give you the more explanation on to these things in the subsequent slides, subsequent sessions, not now, not in the present session, because now it becomes irrelevant as of now. When we start the design, we'll try to focus what are the corners, why we go with these corners, what is the requirement of these things, why do they matter, and how to master them. Because as an analog IC design engineer, you should be able to understand these things more effectively. We'll try to focus on to those things. So yes, so this is basically what we were or what I just wanted to focus. And here comes your final analog IC design flow structure, and this is a simplified version. When we start with the design specifications, we select the topology, do some hand calculations, and then we go with the simulation, do some layout and do some post layout simulation, check whether the specification meets, and then it goes for the fabrication. And this particular these particular 3 points, which will mainly come under the circuit design or analog design engineer, which usually sometimes called as a back end. Even the physical designs or layout engineers. So layout engineers and physical design engineers, they work together. They interact more frequently than with the circuit design engineer. So the layout guys would lay down the do the layouts, and physical design engineer will tell the layout guys how you have to lay the layouts, how you have to draw the architecture, like where you have to place the metals, how you should do the connectivity, what should be the distance, everything would be, and what would be the timing analysis, whether the timings will be met or not. Those things will be told by the physical design engineers, and then layout guy will automatically work on to those things. So majorly in the market, you see three different roles: circuit design engineer, physical design, layout. And there is one more thing. I'll just on an thing. I'll just try to quote over here, DV, which is called as a design verification, where when we actually coming to the before coming to the design specs, you actually or when you have the design specs and when you do the topology selection, you actually start with some Verilog coding and you try to implement all those things with a Verilog and try to do the verification, functionality verification at a Verilog level. And that is basically the digital design verification. So that is also one job role. So design verification comes over here. And then once it goes for the fabrication, and after the fabrication, it again comes back to the circuit design engineer. And here one more guy would be sitting over here, and those are your DFT guys, design for testability. And this is also one more job role which is relevant in the market. So altogether, any engineering graduate who comes out of the college after the graduations would be put in either of these five different or major domains: design verification, circuit design, physical design, layout, and DFT. And altogether, this is basically the analog IC design flow only. And because DV doesn't come under the IC design flow, it has been not shown over here. And because DFT is also irrelevant right now, I have not shown over here. So the relevant things are being marked over here. So this is basically how the structured and simplified version of the analog IC design flow. And this is basically what marks the end of today's session. And I'll try to end this session right now. And from tomorrow onwards, we'll meet again at the same time, and then we'll try to start into the next level of sessions, wherein we'll try to work into the MOSFETs. We'll try to look into the MOSFETs, and we'll try to understand the device structure, and slowly and steadily we'll try to look into the entire aspect of the design. So that's it from my end today. If you have any doubt, any difficulties, you can ask the questions.